Welcome everyone to another evening with the Berlin Functional Programming Group. Today I am very pleased to introduce to you Stephen Diehl. When I first found out about Stephen, he was just a name on a blog, I don't know how many years ago, and he had written a blog with the title, "What I Wish I Knew When I Was Learning Haskell." I think it's gone through a number of iterations at this point, and I think the number of things he wished he had known has grown in that time. But this is a really fantastic resource, continues to be a fantastic resource and a fantastic piece of writing. And what I have come to admire about Stephen and about a lot of developers is that he has opinions. Some developers have obnoxious, annoying opinions. Others are extremely thoughtful, and I think they feel the way I do about Haskell. They find it simultaneously fascinating and frustrating. And I think the frustration is born of a desire to make the situation better and also to make the community better. So this is why I wanted to invite Stephen to speak to us tonight, because I know that he will have a lot of ideas and a lot of opinions. They may not be opinions that you agree with, but we can then have a debate or a conversation. I'm very curious to see what he has to say about the future of Haskell, where he thinks it's headed, more importantly, where he thinks it needs to head. Stephen is the CTO of Adjoint Incorporated, a financial services company, which I think used to do something with smart contracts.
We build accounting solutions. Yeah.
Okay. I just want to highlight the name Adjoint, so you know that their heart is in the right place. And he is, in fact, a physicist as well, and not the first physicist I've met who's become a programmer. And of course, he chose the right programming language, as a physicist would. And I'm very happy to hand over to him, and I think we're going to have a really interesting talk. Definitely come up with some questions. I think a good meetup and a good talk always means good discussion and good questions. Please save them until the end, and we will get to them in due course. So Stephen, thank you very much for joining us this evening, and I turn it over to you.
Okay, lovely. Thanks, Stephen. Okay, so the title of this talk is Haskell for a New Decade. So I'd gotten in the tradition of kind of writing kind of like a synopsis about like what happened in Haskell at the end of the year, every year for a while. And I kind of thought, since this is a new decade of 2020, I'd like to talk a little bit about like where the language has been, where I see it going, because Haskell's been around for a while, and kind of share my insights about what I think are the big problems that I think are worth working on. So really this talk kind of comes out of a lot of conversations I've had with a lot of younger Haskellers who often come to me and ask questions like, you know, I'm 20 something, I'm really excited about Haskell, I learned functional programming, and like, what do I work on? And what are the big areas I can cut my teeth on and, you know, get involved with the community? And so a lot of this talk is going to be kind of a description of what I think are the big problems to work on and what I think are worth working on to make Haskell the language better for yourself and for everybody else. Okay, so if anytime you can't hear me or the audio drops or anything, just let me know in the chat. Zoom doesn't play very well with Xmonad, the Haskell window manager, which I'm going to blame on Zoom, not Haskell. Let me see if I can share my screen though. I posted the slide deck for my presentation. Hey, Stephen, I can't seem to share the screen. Did you twiddle the bit that I can?
You should be able to. You're a co-host. Does it give you some kind of message?
One sec. Share screen. Let's try this. Is that working?
Yes.
Do you see my desktop?
I see. Is it a black hole?
Oh, yes, it is. Okay, that's good.
Okay.
Let me switch over to the deck. Does everybody see the deck?
Yep.
Is it overlapped with my Zoom display, or can everybody see the slides?
I think there's a little bit of overlap.
Okay, let's see if I can move this thing here.
You should be able to miniaturize the Zoom display somehow.
Oh, there we go. Let's see. Okay. Everybody can see my slides, it's fine?
This looks good. This looks good, yep.
Okay, brilliant. Okay, so the title of my talk is Haskell for a New Decade. I'm just gonna jump into it. So the general theme of the slide, I got about 30 slides I'll go through, and then I can take questions at the end if anybody wants to talk about the big problems that I mentioned, my kind of views about where the ecosystem is going, or just anything in Haskell generally, so I can take questions at the end. So I'd ask if you have questions until the end. So my talk generally goes from pessimistic to more optimistic. So if I seem a little bleak at the beginning of it, it gets better at the end. Okay, so I try to be more optimistic, but I wouldn't talk about the cold hard truths about Haskell. So, okay, so I've been writing Haskell for quite a few years now, actually. I started learning it at uni for a while back. I ended up doing a lot of numerical computing solutions for a lot of my physics work at the time. And it turned out that a lot of Haskell is very good when you're translating mathematical code into an executable form. And so I kind of found the language and fell in love with it about 10 years ago now. So that's kind of the origination of most of the writing that I've done ever since then. A lot of it's actually a lot more literal than most people know, actually. Oracle is really like kind of a list of the things that I kind of was learning when I learned Haskell, and it kind of morphed into what it is today. So, and what I find particularly compelling about the Haskell community is I feel like it's a community of people that think about the future and not just about the present. And Haskell has always been a place where we've been able to play with new ideas, new concepts, kind of new ways of conceiving of programming, and we're not constrained by the limitations of the here and now. And that's both a pro and a con of the community, but it's one thing that kind of made me fall in love with Haskell, the language, and Haskell programming in general. So on a slightly more bleaker note, the general profession of software, I think, in the state of 2020 is kind of terrible, and it's getting worse. I think a lot of this is kind of a function of just the era that we're living in. We're kind of at the late stage of Moore's law. A lot of the low-hanging fruit that we're going to get from hardware has been done now, and we only have so many years when processors are going to get any better or any faster. So what that means for us as software engineers is that we've been able to get away with a lot of things for quite a while that we're probably not going to be able to get away with for forever. And I think I'm not alone in thinking that the end user software experience these days is bloated, it's slow, it's insecure, it's increasingly tied to a legacy stack that our industry really can't afford to change. It's really hard to onboard naive 20-somethings into the field and explain why things are as terrible as they are and why we have so much complexity that we've accumulated over the years. And a lot of it is just irreducible complexity that we've added to our stack. And software itself is not getting cheaper to write. In fact, in many ways, it's getting a lot more expensive as time goes on. You need only see the kind of architecture that goes into a lot of these Electron apps that we're building and seeing how bloated the software is becoming. We're cutting a lot of corners as a profession, and it's starting to show, and some of our software is starting to creak around the edges. We're dealing with a lot of software that's intrinsically insecure. It's starting to have a lot of consequences for end user privacy as a concern. And generally, software is not getting any better. I could make a strong argument, and people disagree with this, but that software, in the last decade, has really not gotten all that significantly better. Some things have, but uniformly, I would argue things have actually gotten worse. I'd say open source programming culture has also changed quite a bit. I remember a lot of what open source used to be like back in the early 2000s, and as an open source won in the end. At the end of the day, the only thing is that we won by kind of selling out to large corporates at the end of the day, and open source has largely become the domain of large corporates now instead of a lot of individual contributors, and the barriers to entry and the table stakes to contribute new software these days are very high. I mean, if you wanted to say, build a browser or a new cross-platform GUI engine, the costs for doing that are beyond the reach of any one engineer working on the software themselves. And that has, effects for what we as individual contributors can do now. If projects can only be done by, groups of 10, 15 people just because the engineering involved in it is that involved, then that's going to limit, who gets involved in these kind of projects. And that will intrinsically change the culture of what gets built. And when software is only the purview of large corporates, it tends to be largely dominated by economic concerns and less by technical concerns. So there's a particularly pointed article that I wish everybody would kind of read, and I posted it in the slide notes for this, where Alan Kay attributes a lot of the state of software engineering to that of pop culture. Pop culture is one which he defines as one that's obsessed with the here and now at the expense of learning from the past. It's one that's always obsessed with the current, the latest and greatest, and not learning from the lessons of history. So part of what I want to talk about in this talk is about like where Haskell is and where it's come from, because I think as you get older in your career, you start to become a lot more interested in the historical reasons why software is the way it is. And I've certainly become a lot more interested in the history of why Haskell got to the point where it is. So that's the bleak slide. It gets happier from here. So that said, software as a profession has really only been around for maybe 30, 40 years, depending on how you slice it. If you think of like what medicine was like when it was 30 or 40 years old, here's a picture in ancient Venice, people bloodletting, putting leeches on, and that was what counted for medicine. And really, if you think of software as basically being in exactly the same kind of bloodletting and leeching stage, then a lot of this kind of makes sense. In about 300, 400 years, we're going to be like medicine is today on the right. And if you understand kind of the evolution of software as being just the growing pains of a very early field, then a lot of these things don't seem so bleak. They just become part of the natural cycle of the development of a human field of study. And so it's important to put everything in context. We're getting there, but there's a long ways to go before we become a true science field. So that said, we really got to think about like what are the timescales of progress, and this is a question I've been thinking about for a long time because I spent a while thinking about like why things aren't moving quicker than they are. And the answer is software's really never moved that quickly. The lambda calculus was was invented in 1930, or I guess it was discovered in 1930 if you're a Platonist, I guess, like Phil Adler's. That's not that long ago in the grand scheme of things. I mean, that's less than a century ago. The second order polymorphic lambda calculus was discovered by Girard in 1972, and that's the foundation of Haskell today. Probably the prime example is, garbage collection was basically invented in very early Lisp dialects back in 1959, and that didn't really find mainstream adoption until Java in around 92. So 1959 to 1992 will kind of give you a sense of like the timescales involved in something as seemingly mundane and as a garbage collector. It takes 30 years to get into the mainstream. And so, if you think about the ideas that we use day to day in functional programming languages, the fact that they find their way into mainstream languages like, Rust and Swift and TypeScript and everything on like a 10 to 20 year lag, that's really not that bad in the grand scheme of things because, traditionally it's taken 20, 30 years for things to get better. There's this law called Probstik's law, which says that, it's kind of a corollary to Moore's law, which says that improvements to compiler technologies double the performance of typical programs every 18 years. That's a long time, 18 years is, oftentimes like the length of an entire software engineer's professional career. If it takes that long, double, just be aware of these things. So, and I think, it's important for us as software engineers to kind of question, whether there is actually progress in the field of programming languages. We don't ask questions like, is there progress in literature, or is there progress in fashion or philosophy? We just have kind of schools of thought that develop, and there are debates about which ones are right and all, but there's no kind of, gradual arc of history that lends toward bigger and greater things. And, in software, we always like to pretend like things are getting better, but maybe that's the wrong question to be asking. Maybe our software industry is basically just more like fashion than it is like engineering. Question. Timescale of progress is basically very slow. So where's Haskell come from? Haskell goes all the way back to 1989 in some capacity. So that was a very, very different time in computing. That was the year the Berlin Wall fell. Computing back then was this Apple Macintosh SE30, the 804, 886 was just released. MS-DOS 4.1, Lotus Notes at CERN in Switzerland. There was a proposal for this little thing called the Internet. Turned out to be a pretty good idea. And then, the first Haskell language, the specification for what would become GHC eventually, was first developed at that time by a bunch of academics. And, that's a long time ago. Haskell is basically as old as, Java. It's older than Python. That's the kind of time scale involved in this. We like to think of it as being a very kind of, very recent new language, but in fact, it's actually quite old. So this is a very old Haskell logo from way back in the day when there was a voting contest about what should be the official Haskell logo. And I was kind of sad that the narwhal itself didn't win because that was a far superior logo in my opinion. So the present today, some things have changed, but a lot of things really haven't changed in about 40 years, really. We have a brand new compiler, GHC 8.10.1, just came out a few months ago. It's a brilliant piece of engineering. We have an amazing, stable, industrial strength compiler that's beyond the wildest dreams of what people would have thought about 30 years ago in the Haskell community. We have an amazing, fast, concurrent runtime in Haskell, which is a remarkable piece of engineering that multiple people have contributed over for the last 20 years. Generates some of the fastest native code from any kind of functional language out there. We have build tooling, which has gone from adequate to actually quite good in the last few years. Back when I was first learning Haskell, you used to have to unpack tarballs into directories and like manually link all your programs together. So really that's the kind of baseline that I've started at. And really anything above that is really kind of been an improvement, regardless of how all the evolution of Cabal has gone through. What we have today is actually really quite good in the grand scheme of things. GHC is growing a really, really nice set of extensible compiler plugins. So if people haven't kind of explored the compiler plugins inside the GHC infrastructure, take a look at them because they're a remarkable piece of ways of extending a compiler that I've rarely seen in other languages. You can extend the type checker with new type checker plugins. You can extend the front end. You can add new core to core passes. You can add new surface syntax. You can take annotations and enrich code with them. There's an amazing amount of work that's done there. And GHC is a really kind of open compiler. Like you can directly link against the GHC internals. You can extend it in new ways. It's really a remarkable piece of engineering. We have dependent types now in Haskell, at least some measure of them. We can do lots of remarkable type level programming. GHC really is the only kind of mainstream programming language that you could actually use like in Anchor and actually experiment with kind of very, very recent advances in type system research. There are other languages which are more advanced, obviously, Agda and Coq and things, but obviously they're not tools that you would then use like in your day job at all. So Haskell's always kind of straddled that line between being a test bed for new research and also being a practical language. The editor ecosystem is improving drastically in the last, I'd say, 12, 16 months. There's been a lot of very, very heroic work by some people kind of pushing forward on some of the language server or some of the tooling around the GHC APIs. And I'm really excited for that this year. I think things are going to we're going to see a sea change because people have been complaining about the lack of an IDE for a while. I think that may change in the next 6 months or so because things are at that point now. And then the thriving package ecosystem. Haskell package for all of its good and bad has a lot of really, really, really good code in there that people contributed for the last 20 years or so. And the ecosystem is really amazing in many ways. So that's all the good things that we have now. So we've come a long ways in the way. So when you think about like all of the deficiencies in Haskell, think about the language has been around for 30 years and it's still evolving, and look at all the things that we have now with such a small community. Haskell, if you take your average kind of Python library for doing like genomics or something, you pick just a single library, the entire user base of that one library inside of Python is probably larger than the entire Haskell ecosystem as far as number of users. So, the amount of things that, the Haskell community has done, being such a small group of people, is actually kind of remarkable. And, Haskell really gives us the power to kind of punch a lot above our weight as far as being a very robust platform for doing the things that Haskell is good at. Okay, so this is kind of a model that I like to always talk about when I talk to younger engineers about how to envision the PL ecosystem or the language, sort of the ecosystem around a language. So, you got to think about a language community as kind of being an economic engine. It's a set of ideas that people gather around and that they use for various purposes to achieve different ends. But it's this flywheel that produces value for all participants involved. And I kind of label these things around like 4 different dimensions along the flywheel. So I kind of have the research, the social, the knowledge transfer, and the economic. And in order for a language community to be successful, the metaphor I like to use is that there has to be kind of uniform torque across all of these dimensions. Only then will the kind of flywheel spin and produce value for all the participants. So intrinsic to the Haskell ecosystem is that we've always had a strong research community. These are folks that are working in academia. They work on the GHC compiler. They work on producing new research on systems. They teach courses to undergraduates at university, and they just participate generally in the low-level evolution of the language. So that contributes a lot of the development that spins this kind of cycle of the quadrant of the wheel. That in turn really feeds into what I call the social aspect of the language, which is the online community, the group of people that participate, who love the language, who contribute code and discuss about it constantly. And with Haskell, we have a very vibrant community that's kind of split across a bunch of communities. And that leads to things like scholarships for conferences and diversity outreach and meetups and conferences to be sponsored. And that's a big part of it because software at the end of the day is the product of people, and software is made of people at the end of the day. And that aspect really kind of contributes to what I call the volunteer groups. So the more people that are kind of exposed to these kind of new ideas through these in-person meetups or through these outreach, this contributes to volunteers, which feed into the open source ecosystem, and they participate in the transfer of that knowledge that they get from in-person to other people across the internet or to other participants in open source. And knowledge transfer is a really, really important part of growing a community. It's something that we as a community have not done so well. So this has always been kind of one of those things that I've been kind of focusing a lot of my time on, because I feel like documentation is kind of one of the easiest way to kind of bootstrap more interest in the language. And I've certainly written a fair bit of documentation at this point for all the things I wish I knew in learning Haskell. And, but it's really important that more people start getting involved in that, because when you're learning a language, it's important that once you climb the ladder, you got to make sure that you lower it down for other people to climb up behind you, because that's the way we get more people to have the same knowledge that you have. Because at the end of the day, we all want participants and friends to collaborate with, and that's a big important part of it. So ultimately, the knowledge transfer leads to more employable Haskellers at the end of the day, people that are going to enter the job market and have in writing Haskell professionally. And Haskell's also been particularly weak in this aspect for a while. Industrial users are essential to languages these days. There's no way you can have a successful language without having industrial involvement in some way, because the cost of software development now is untenable to be doing on a pro bono basis. And so an active ecosystem of corporate sponsors, an active job market, support and training through consultancies, and just corporates that are willing to sponsor open source library development are essential to the ecosystem these days. And that in turn produces cash flow. Unfortunately, language ecosystems require a constant inflow of cash, and the kind of basic economic reality of this thing is that in order for a language ecosystem to grow, they require a constant influx of cash to make all of this happen. And that ultimately comes from the market economy, which allows development to happen. And so Haskell has some of these kind of very well off, but a lot of the wheels are kind of stuck. And so oftentimes they need a little bit of a greasing to kind of spin the wheel along. So, but I think when we talk about language communities, it's very, very easy to kind of fall into this fallacy to reduce all progress down to a single aspect of this. So it's very easy to say that, if only there were more jobs, then the whole wheel would spin. Or only if the community were more diverse, the whole wheel would spin. But it's really, it requires all 4 aspects of these things for the community to function. And they all have to be kind of working in parallel. Otherwise, we end up with a kind of stagnant ecosystem where nothing happens. So a PL community is a group of people who share in the success of a common idea. So if you think about that way, this is a model, and I think it's a pretty good one to think about what's the way to allocate our time and our resources as open source software engineers to the ecosystem. So what, if anything, is Haskell good for? This is a question, it's a hard question I have to ask for myself. There are not many very big success stories for Haskell. For a 30-year language, it's very difficult to find even one company where you could isolate it as being a success story. I mean, people always point at, a few of the banks here in the UK and all that. And I think if you dig into that, you'll see, is that really a success? There might be a group of, a small group of people that maybe wrote Haskell at some point in the past and then maybe contributed some code, which is then sitting there bit rotting for the next, 10 years, or there's one person there who's a prominent member of the community. But none of that really contributes to kind of the growth of the ecosystem. And I think the question that people that are involved in the community for a while have to ask is like, what is the niche that Haskell's actually good at? Because I have difficulty labeling it. People always point at compilers as being kind of an area, but there's not that many success stories for Haskell compilers out there. I mean, there's PureScript, there's Agda, and there's Idris, all of which who probably have a combined user base of, maybe a few hundred people in the world. So is it a success? Yeah, but not by any means of the rest of the industry by any means. Is document preparation. It's Pandoc, which is an amazing tool. But Pandoc is one library. It's an amazing tool, but is that the only thing that Haskell is good for? Because it seems to be the most prominent library that everybody can kind of recognize. Prototype for papers, proof assistance. Just think about this because it's a hard question, and we need more success stories in the industry for us to be able to point at, because momentum breeds more momentum, and Haskell really kind of lacks industrial momentum at the moment. So Simon always has this really poignant slide in which he has the kind of the growth of a language over time. And, he always compares academic languages typically have this kind of parabolic arc where they kind of have one or two users and they die. And then some languages basically, go steady state for a while and they basically just, fall off at a few users. And then there's a few languages that cross the threshold of immortality, as Simon says, which is the complete absence of death. However, Simon's talk always kind of stops there, and the complete absence of death certainly has multiple readings. So the complete absence of death can also mean like there's this kind of zombie form of immortality in which the language cannot be allowed to die, even though it probably should die. This is the kind of COBOL route in which the language kind of persists forever because such critical things are written that it can't be let to die. Is that a desirable state? I don't know. Then we also have the kind of sort of Time Lord immortality state where the language consistently regenerates itself over time. So those who don't know, Time Lords are the Doctor Who series where David Tennant here is an immortal being that travels through time and space. And I prefer the kind of sort of Time Lord threshold of immortality where Haskell is continuously rejuvenating itself in new forms and new manifestations as time goes on, rather than the kind of zombie form where there's just a few practitioners who are left keeping something that should be dead alive forever, like the COBOL way. So think about that when you're thinking about the future of the language. So avoid the zombie mode, think more Time Lord. So I outlined 3 different features that I see Haskell kind of going on, and these are kind of up to speculation about like where I see the ecosystem going, but the ones that we have some historical precedent for how we've seen other ecosystems go. So the one feature I see is kind of stagnation and sclerosis. So basically where the language more or less decays and is unable to be changed in meaningful ways for a long time. So it remains very rigid, that's the sclerosis. So I kind of isolate this as the standard ML model, where standard ML was actually a very beautiful language, but more or less is not really used at all anymore. It obviously inspired other languages as successors, but in and of itself was not a spectacular success by any means. It was left as kind of an academic curiosity for students studying university and then never use, which is a shame because ML had a lot of brilliant ideas in it, and it wasn't heavily invested in by corporates as well back in the early 90s. But this is kind of prototypical for the stagnation model. So in the stagnation model, the barrier to entry for GHC development remains impossibly high. Such that we can't onboard new users onto developing it. And so, at a certain point, most engineers that do open source eventually kind of, shuffle off and, don't maintain the code that they used to once more whether by age or by just retiring. It's just intrinsic to just the human life cycle that open source contributors don't contribute forever. What really worries me a little bit is that the Cartesian product of all of the language extensions and all of their semantics may eventually kind of exceed the human cognitive capacity for like any one person to maintain. There's already kind of signs that the language has gotten the Cartesian product of every single language extension and how they possibly interact with every other language extension is not something that many people can hold in their head. Even brilliant people like Simon, it might be a point where the language has sort of reached its carrying capacity for new novel ideas, and it's at a level of complexity where not one person can maintain it. And then, in that kind of situation, the hackage ecosystem may bit rot into an archive of, very clever ideas, but, ultimately ideas that no longer compile anymore. And then a lot of ideas will be lost. We already see some of that from, the early 2000s, where there's a lot of really brilliant Haskell code that was written that really no longer compiles anymore because the Haskell ecosystem moves so quickly. And, Haskell is not the same as it was back in '98. So the kind of steady, kind of the middle ground. So this doesn't quite have the same kind of decay we see, but it's kind of, things just stay the way they are now. That's not the most horrible fate for a language, but, think about it this way, a small group of students learn Haskell at university, they find it very interesting, intellectually stimulating, but then ultimately they leave university and go off to write Java in industry and never touch it again. That's not the worst fate. At least they're still learning the language and they're still, taking the ideas and taking them off into industry to do things with them. But, by no means is that success. The German Haskell meetup has always been really lively, but, where there's a bunch of people that can meet up a couple times a year. They talk about the latest like functional Perl paper. This is fun, but it doesn't move anything forward as language. You want to see kind of a more thriving ecosystem. The language like Haskell today is blacklisted at some very large San Francisco companies simply because it's considered unfit by production for most of the CTOs there. Laziness is often considered like, the boogeyman. Laziness is this, this monster that's going to come and steal your children and, cause space leaks everywhere. And, it fundamentally should prevent all Haskell development of any kind of scale because laziness is just evil. That's a meme that exists out there, and I don't see that going away. There's another dozen papers about building red-black trees with dependent types. This seems to be kind of the canonical thing that we do with dependent types. We don't build anything real with them. We just build, algorithms to sort red-black trees. It's people have been doing for 20 years now. We continue to debate about terminology in the language. So this goes on since the beginning of when Phil Wadler added monads to the language. People have been debating whether we should call them monads forever. It's not an interesting debate anymore. They are what they are. And they're intrinsically a little bit difficult people to learn. But this is just constantly the debate that we have whether monads should be called warm fuzzy things or whether the names of terms that we have in our programming languages should immediately convey intuition by mapping them down to like real world objects, or whether we can use terms from abstract algebra because they're more concise. That's not a debate that's really interesting anymore to most of us. And then there's high turnover at a lot of small companies. So in a state where there's not much support from the larger industrial ecosystem, ultimately you have a lot of turnover from smaller companies, and that's not really good for anybody, really. We want to have a Haskell ecosystem where people can, write the language and grow in their career simultaneously and, maintain a reasonable standard of life while trying to, work on the tools and programming languages they want to build. So. And then, the question I think is the more optimistic one, and this is the one I don't have the answers to, but this is why I'm giving this talk is, the growth, the renaissance, the, utopia model. What does that look like? Because a lot of people have different ideas about like what that means. Some people believe that Haskell really as a language should, kind of stick to its niche and just be a language for, compiler development and language experimentation. Others want to see more widespread adoption where the user base grows maybe, doubles or triples or grows polynomially or exponentially. And there are differing views on that. For me, I say anything uniformly better than what we're doing right now is success. But I'm going to kind of outline what I think are the areas that we can improve in as an ecosystem and like what are the big problems to work on to get us to that point. But ultimately, this is a question that you have to ask yourself about like, where do you want to see the language go? So we're in a new decade now, 2020. It's a fresh start. I'm a big believer in open source. I think open source development drastically outperforms the market. The things I see being developed by just a few small people, groups of people who are really raring to work on a project can, transform an entire sector and create new industries. I've seen it over and over again in my career where one or two software engineers are vastly privileged. It's like equivalent of like having a country, like, an entire, country is fed by like one farmer. That's like the equivalent of like the leverage that open source software can have. One library can oftentimes create vast new amounts of companies and transform entire industries, and that does happen. And that's really unique to our profession. It doesn't happen elsewhere, and it's something that makes open source really special. But it's important to think about open source. It's open as an open door, not as an open bar. Open door means you're free to come in and contribute, and but not free to just universally take from the bar. Think about open source as being something that you participate in, rather than something that you just take and extract value out of, because it doesn't work if everybody kind of just extracts value out of it. We have the same kind of tragedy of the commons that we see. It just burns out open source developers. So you have to give back. And so, like, when you're thinking about open source and generally your career in general, as a participant in an open source ecosystem, you should leave the campground better than when you found it. You should contribute the documentation that you wish you had when you were starting Haskell. Think about contributing the libraries that you need for your job back to the ecosystem. And this is the biggest thing I tell sort of younger Haskellers, is that you do have to do open source. Like, the whole ecosystem as a whole just doesn't work unless a lot of us do this, because this is what drives our profession forward more so than any one corporate will do, because these kind of projects, these kind of endeavors span our entire industry. So we have a new generation of peers. In some ways, the new generation of 20-somethings that are coming out of university are different culturally in some ways, and there's different kind of mentality toward open source. But as you're starting to grow in your professional careers, think about giving back and thinking about starting new projects and contributing back, because it's really important. And so the next couple slides are like my personal answers about like what I think are the big open source epics that we should be working on for the next decade. And obviously this is subjective, but this is Stephen's opinion on it. So to put things in perspective here, Haskell does not exist in isolation. Haskell is part of a family of languages. It's not clear precisely what the Haskell-like family is, because people say intrinsically, like, Haskell, it has to be lazy in order to be language. But I'm saying, semantically, there's this kind of fuzzy category of Haskell-like languages, whether they're related to their syntax, or pattern matching, or their embrace referential transparency in some way. Some combination of those three factors kind of forms the amorphous category of Haskell-like languages. And it's important to look back at the history of Haskell, because GHC Haskell is not the only Haskell compiler. It's just really the last surviving one, really. I mean, there's been a variety of ones that have been developed over the years: UHC, JHC, Hugs. There's a whole variety of ones going back to this Intel Haskell compiler. Most of them are dead projects at this point, but it's not, definitely you can kind of see the marks and the cross-pollination that they had on the whole ecosystem. So right now there's really only just GHC Haskell, and GHC Haskell is not a specified language. GHC is Haskell 2010 plus a mountain of extensions, and that's what kind of defines, the implementation defines the specification at this point as of 2020. So, and then off of that we have the kind of what I call the second generation of languages, which are languages that have drawn heavily from Haskell as an implementation. So PureScript being kind of the most notable one. PureScript shares a lot of similar ideas to Haskell. Obviously, it's not a lazy language. It's a call by value language. So they share some similarities. Obviously, PureScript is itself written in Haskell. Idris obviously is experimenting with different kind of extensions to the type system along the pen route, type route. Agda is also a brilliant example of research language. There's some interesting chaps in the States working on this Unison language, which is doing some novel ideas around distributed computing. And then there's also this Discus language, which I think is out of some Australian university. And, so Haskell, being a successful language is starting to spawn an ecosystem around it of successor languages. And this is only going to happen more because Haskell is kind of a branch in the language evolutionary tree. And it's kind of evolving into this new ecosystem. And then Idris too is actually evolving. I call this kind of the third generation of Haskell-like language, which is kind of the next evolution. Edwin's doing of Idris, which I think he's going to be talking about in 2 weeks on Ceph Meetup, actually. So it's really important for the next generation of languages to kind of learn from the mistakes of the past. And I think Haskell as a language does a lot of things that in hindsight we probably would not do again. There are certainly some very, very quirky things in the language that are very, very difficult to change now because you can't break the entire ecosystem, obviously. But obviously the name spacing of records is kind of a source of perennial pain that's slowly getting fixed, but it's taken 15, 20 years now. The implicit prelude, I think, is probably not something we would do again. Probably not. Most languages have kind of moved away from that kind of model. The numerical tower in Haskell was a bit quirky for a few different reasons, and probably would be split up into multiple classes if we're done again. Probably a language would probably build a module system, either first class or second class one, intrinsically to the language. Obviously, Haskell's tried to do this at link time with all backpack system, but obviously that's kind of, suboptimal in certain ways. Obviously, a lot of work around building module systems, and if you were designing a language from first principles, that would be one of those things that you would kind of try to break into from the start rather than trying to bolt it on afterwards. And this open question about whether the core calculus should be dependently typed or system F based, and that's an open question. I don't know. But really, we should think about the fact that there are these languages that are kind of building on top of Haskell, either as the base implementation for bootstrapping, or as kind of evolution of Haskell itself as being progress. When the language mutates and evolves, that ultimately leads to bigger and better things. Some of them will die off, but that's just evolution, and I consider that to be progress. So really, the language family of functional languages, we're very early on in the discovery of what that should be. We don't know most of what the functional language design space should be because there's basically only a handful of functional languages out there. We have Haskell, we have OCaml, and then we have a few experimental academic languages that really nobody uses in the large, and Scala, I guess, too, as well. But, really, there's 3 languages. I mean, look how many imperative languages there are kind of going across and exploring much more of the imperative design space. There's only 3 functional programming languages. It is, comically unsuccessful or comically unpopular in industry. And we just don't know a whole lot of things that we don't know about them because nobody's built more languages yet. We don't know what programming in the large and functional programming looks like because we're so early. So more compiler experiments are a good thing. And Haskell's always been kind of a very active breeding ground for new experimentation. That's a really good thing. Ultimately, there's very little that you can say about how a language will succeed a priori. Like all knowledge we have about programming in the large can only be derived from experience. And there's only so much that you can say from first principles by looking at the semantics of the language. But the one thing I will say about in the functional programming space is that the success or failure measured by a number of users, in my case, that metric, is highly correlated with the ability of the compiler itself to generate efficient backend code. So toy languages that are interpreted and slow really don't go anywhere, really can't go anywhere until they generate efficient backend code, because ultimately, if it's going to be used in industry, having an efficient code generator that's on par with at least interpreted dynamic languages is kind of a necessity. So okay, on the topic of kind of larger, more things in the Haskell ecosystem, the big epic I think this coming next 10 years ago will be kind of figuring out like what the kind of spiritual successor to kind of the MTL way of managing X would be. So if you program in Haskell at all, you'd know that we have this kind of system called MTL. It provides a set of monad transformers, which basically allow us to compose effects at the type system. And manage, basically separate pure code from impure code and then track the specific effects that code is doing inside of a block of code. So monad transformers are a very kind of interesting way of manipulating or having a type safe way of managing effects, but they come with some very, very serious limitations. There's definitely some performance overhead from dealing with MTL. In the form of dictionary lookups. Monad transformers themselves don't commute. And they're just very difficult to kind of build new extensions to MTL. So this is kind of n+1 monad transformer problems where if you want to extend with a new effect, you have to implement a whole suite of type classes for every single new class that you want to add. And this ends up with this massive amount of code below, which is largely a bunch of like lifts or boilerplate. And right now that all has to be either generated using template Haskell or just written manually. It's suboptimal for various reasons. So fortunately, from the theory side, there's definitely been some more work on how to better manage this problem with things that are not monads. And so there's these algebraic effect handlers that have been kind of floating around for the last 10, 15 years now. And we're only kind of recently seeing some of them being used in the large. So there's some really brilliant packages, polysemi and this fused effects package, which have really kind of taken these ideas and kind of run with them to the point of getting them fairly close to being able to run in production. So they both take kind of slightly different variations in the design space for these things, but both of them are getting to the point where they're, ready to kind of see some live action in some real code bases. Still lots of optimizations to do. Some of them still require some like GHC type plugins to kind of handle some of the inference and all, but things are getting there and they're moving along. So at the bottom here, I kind of showed an example of how do you do effect tracking inside polysemi. So this is a example function that has a type level list, which allows us to annotate the function with a list of the effects of the type system. And so those are all the ones that are tracked inside of the body of this do expression. So that's what a effect handler looks like inside this one particular library. So, but more people should really kind of play around with these libraries, kick the tires in, and just try to use them, because I think this is the way things are going to be going in the next 10 years, because I think MTL is not going to be with us forever, nor should it be, I think. We need to move on a little bit. So this is kind of if you're looking for a project to contribute to, or one that you're trying to, test to see and kick the tires in, then these effect handler libraries are really important for the ecosystem. Okay, so GHC. GHC is a very big, old, quirky code base. So it's a very lovable code base in some ways because it gave us all what Haskell is today. But if you go look inside, there's definitely some, shall we say, some dark corners inside of it. It does some very, very strange things for some historical reasons, and like this fast strings and all sorts of custom types that it rolls, which are left in there for various reasons. But GHC is a code base that once you reach a certain level of familiarity with the Haskell language, that I really encourage you to kind of just delve into, because in order to understand Haskell and like what makes Haskell Haskell, you really have to dive into GHC. And I encourage every Haskeller to pull the GHC source tree from GitLab. There's a really nice guide from ghc.dev where it kind of walks you through the entire process for compiling this language from source. And it's important for you to kind of see like what actually goes into bootstrapping the compiler, how GHC compilation works, how it interacts with GCC, how all the pipelines work, because GHC is just written itself in Haskell, and it's actually not terribly advanced Haskell. It's voluminous Haskell in the sense, but there's not a whole lot of, like, it's written in a very Haskell 98 style. If you sit down and read through most of the modules that are probably not the type checker, with a bit of time and patience, you kind of get the whole gestalt of what's going on. And, it's not as scary as it was. So, GHC is not a scary code base. Really, you should delve into it. It's very beautiful in some ways and sort of quirky in others. But also subscribe to the GHC devs mailing list. This is one I've been subscribing to for years now, actually. And, you'll learn a lot about how the sausage gets made and how all the releases are coming together. And it's really important for us as a community to kind of understand like upstream, like what's actually happening, because there's a lot of very interesting and really groundbreaking stuff that's going on. And you have the chance to kind of influence decisions that are made upstream if you get involved in that. If something will affect your company's code base upstream, you should be aware of those things. So GHC development sustainability kind of worries me a lot. So GHC is not isolated from the rest of the whole open source ecosystem, and that developer sustainability is an issue. GHC is maintained by a very small group of people, very small. I think there's really only one full-time person maintaining GHC in the sense that it's their day job. So that should sort of scare you in some in some ways. And I honestly don't know how long this is going to be sustainable for, unless more people kind of start to get involved in GHC development, because that's a necessity for the whole language ecosystem to evolve. And I don't know what it's going to take, but that's kind of if you're a young aspiring Haskeller and you want to get involved in something that will be truly meaningful for Haskell, the language, GHC development is a noble calling. GHC Haskell is probably not going to be everything for all people forever. So this has been kind of a topic of discussion for a while, but it's sort of a truism if you think about it. The language, when it is successful, will attract people who are going to be using it for different purposes, and ultimately their needs are going to diverge at some point if the language ecosystem reaches a level of critical mass. It's not a question of whether if this is going to happen, it's just a function of when, if the language is successful. And I think in the absence of a new specification, that may happen sooner rather than later. So that's an open question, obviously, something that probably sparks some discussion, but I'm happy to talk about questions about that later. So GHC itself may be on a trajectory to kind of being unusably slow for a lot of industrial code bases. So if you try to use Haskell production or try to run it in like a continuous integration server, you realize that compile times can take quite a bit of time depending on how complex your code is. It's not unheard of to see compile times lasting hours. So in the grand scheme of things, like languages like C++ and certainly Java code bases are not immune from slow compile times, but GHC in particular has some pretty existential problems that make it rather slow when you kind of start writing Haskell in the large. So it's an open question how this is going to impact the language evolution. Ultimately, if we're limited by the size of the code bases that we can produce, that's going to be kind of a turnoff for quite a few industry users who are looking for to build large code bases for the ecosystem. And so fortunately, the problem itself is actually kind of isolated to a very one subsystem of the compiler itself, and that's the simplifier. So this is the really, really non-trivial bit that kind of takes a lot of your core code and then transforms it into a more efficient form of itself by doing lots of things like floating let statements and doing inlining and all that. So a lot of the big wins are actually isolated to this one subsystem. So this is a nice thing because it really boils down to not a hard theoretical problem, but just a lot of engineering work. And unfortunately, there's probably just not enough time in the day for a lot of the current GHC developers to kind of focus on those things. But given the course of a decade, this could resolve itself with enough kind of engineering effort put toward it. But we don't want to be in a situation where in 2030 we have to allocate these 6 terabyte AWS instances basically just to compile our code. That would be horrible. We need GHC to kind of be slightly more frugal with memory, and that's kind of a problem that a lot of industrial users encounter right now. But it's a tractable one, but it's one of those ones that kind of is a problem for this decade. Okay, so this is a cool project as well. Grin is a project written by 2 friends of mine, Andor and Kasab, who are 2 Hungarian Haskellers. So this is a really ambitious project that's basically trying to build a retargetable and reusable functional compilation framework for multiple functional languages. So this grand idea is basically that we can have this target language, which Idris, Haskell, Agda, any kind of new research language can target, and it supports both lazy and functional compilation, and it takes care of all the compilation from this intermediate representation all the way down to LLVM. So they actually have a really interesting working prototype stood up that kind of compiles against GHC 8.6, compiles against Idris, and I know personally that they're looking for more volunteers, for people who are interested in doing compiler development to kind of help out with this thing. And it's really kind of continuing on in the kind of LLVM tradition where we kind of build compilers as these modular sets of libraries which we can then reuse across different tools. And you could think of basically Grin as basically being the functional target that makes LLVM a bit more targetable from our functional domain rather than trying to target LLVM directly. So I highly encourage people to look at this project because it's terribly ambitious and they're good guys working on this. So this is probably, I think, one of the most important things kind of for cross language collaboration. So editor tooling is definitely an area where contribution entry is very, very low. And so this is, there's a lot of low-hanging fruit in this area. So in the last couple of years, GHC up, the kind of bootstrapping tool, has gotten a lot better. So like no longer is there a problem like how do I install GHC? Now this, you know, the canonical way of doing this, you can do, you know, GHC up install, you know, GHC 8.10, Cabal, all that jazz. And you know, Cabal itself obviously has always been kind of a point of discussion in the ecosystem, has really gotten much better. So if you've been kind of dancing back and forth between Stack and Cabal at all, you know, definitely check out what Cabal is doing now, because I think a lot of the code bases that were kind of using Stack previously can switch to Cabal, and because things have gotten a lot better with the whole new V2 build system, and really things are markedly improved. And I think there's no reason that we should be talking about Cabal hell anymore, because it's not really a thing like it used to be. So linking against the GHC and the Cabal APIs used to be kind of a royal pain, but there's been a lot of tooling that have both on the GHC side and on the user space side that can make this a lot easier now. So GHC API is not stable between versions of GHC. So if you're trying to write a piece of code which itself links against GHC, you're going to have a lot of like C++ macros in there to kind of disambiguate between different versions of GHC, and it gets really ugly really fast, because like the arguments of the function will change between versions. And if you want to create like compatibilities between those, it's a real pain. So this is a lovely library called GHClib, which tries to abstract away some of the API to present kind of a uniform interface between versions, which is actually quite useful. And then you can version it based on the specific GHC version that you're building against, which is quite useful. So this kind of abstracts away a lot of the complexity of dealing with GHC APIs, which makes a lot more tooling a lot more easy to write, because before it used to be just anybody who's trying to compile, like say, you know, a GHC mod from source will kind of hit up against this, you know, compiling against GHC used to be really hard. There's also this lovely library called HIE BIOS, which some editor tooling uses internally, but as part of the GHC API, there's this massive kind of global GHC session object that gets set up with all of the, you know, link time dependencies and all of the paths necessary to compile kind of a unit of Haskell code. And before that, used to be kind of a royal pain actually kind of set up in practice. But there's this lovely library called HIE BIOS, which basically abstracts away over all of the path management between both Stack, between Cabal. It also has some support for Nix, that you can basically point out these cradle objects, which then instantiate the GHC session abstractly. And it presents a kind of uniform interface across all of those things, which makes writing tooling that uses Cabal a lot less painful than it used to be before. So this is a really brilliant library. And if you're coding against the GHC library, don't be setting up your sessions manually. Use this library. It works wonders. And there's also the Haskell language server, which has been merged into the Haskell org now. So that really is coming along quite nicely. And there's been a lot of work upstream on getting the Microsoft language server integration with GHC tooling. So in particular, inside of GHC 8.8, there's these new Haskell editor integration files which have landed, which allows GHC to dump quite a bit of the metadata it stores internally about compilation of individual Haskell modules down to a file, which can be stored and then queried by your editor tooling. So if you haven't enabled this inside of your Cabal file for your project, if you have this in your GHC options section, if you have to add a flag in here, obviously it's only available on newer versions, but you can say fret IDE info and then specify the IDE dir, and it'll write those files there, which will be able to be queried. So this will be used quite extensively when the Haskell language server is more mature, but this is something that you can do today and start getting experiment with, because it's going to be part of how our editor tooling works in the future. So this is a really big progress, and like in a few years, like Haskell editor tooling could be, you know, light years ahead of where it is now, and it's exciting. So I think we're really in kind of a renaissance for this. So another area that I kind of is a bigger area, but it's kind of one that kind of fits into the kind of larger macroeconomic space of where software is that machine learning is a phenomenon inside of programming at the moment. So I used to come from the Python ecosystem, so I used to do a lot of numerical computing, and it's always kind of a little bit curious to me that over in the Python ecosystem, a lot of programmers are basically slowly reinventing functional compilers on top of Python, and this is no more clear than when you kind of dig into the documentation for, say, things like JAX or the Google library or Swift TensorFlow and TorchScript, and you'll see like giant type signatures for Haskell laid out through the documentation, or talking about how they're transforming everything into, you know, pure functional SSA form, where we have like let statements everywhere. And so like basically a lot of these functional tensor compilers that are being built over in that side of the ecosystem are basically reinventing for ideas from FP that have been around for 20 years. They're just doing it on top of the Python ecosystem because there's availability for tools like NumPy and all that. But ultimately, the idea should not be very foreign to most of us Haskellers. And since a lot of them are working on these sort of multi-language intermediate representation, there's definitely some, small window in which if you're keen on, building editor or Haskell integration to this kind of ecosystem, there are entry points doing that now. Whereas before you'd have to like link against the C++ TensorFlow library or, do more complex things. These things are trying to become a little bit more extensible and more modular because, I took a look at this graph of all of the dependencies between different array libraries, tensor libraries, and intermediate compilation forms, and it's an absolute mess of different hardware specifications. You see like CUDA and MLIR, and different ones are owned by different companies, and there's a lot of compiler work that's being done over in that ecosystem, which is starting to open up. And so I'm saying that this is kind of an interesting area to start collaborating with people outside of the Haskell ecosystem, because there's definitely ideas from the Haskell space, which are translating over to there, and there's ways to meet midway. So in particular, this MLIR project, which has become a submodule on the LLVM project, is aiming to be this kind of functional graph rewrite engine on top of LLVM, which is going to be a higher level target for ML frameworks. So this is still a really nascent project, but obviously Chris Latner is obviously pushing this forward personally, and it's starting to see some traction, and it's going to become an interesting kind of intermediate representation for a bunch of compilers in the future. So definitely look into that, because I think it's going to be important in the next 5-6 years. Also, there's also the HaskTorch library, which is Haskell bindings to the PyTorch C++ bindings. And then most importantly, out of Google, there's this really, really interesting functional compiler in the ML family, which is basically a rewrite of some of the JAX core inside of Haskell itself. So there's some really clever chaps, and some of the old actually PyTorch developers themselves are actually working on this new framework, which could eventually become really, really big, interesting way of compiling tensor expressions from inside of a Haskell-like language. So take a look at that and definitely keep an eye on that. Okay, and so this other area, so this has been kind of my pet for a little while. This is kind of an area, a niche branch of computer science that I've been kind of interested in for quite a while, because it's been kind of theoretically possible for a while, but it's only in the last couple of years that this kind of become seemingly practical. So there's this branch of cryptography called verifiable computation, which effectively concerns itself with you have some sort of function that you want to prove to an untrusted party that you've evaluated correctly with some public set of inputs. And you want to basically prove to, Alice wants to prove to Bob, she'd run f of x, given a specific x correctly, and given a specific output of f. And so this has been kind of theoretically possible for a while, but it's been very, very computationally expensive. But there's been some recent advances in abstract algebra and cryptography that have led to some very, very efficient constructions, which have kind of put this in the realm of being computationally tractable for a while. So these are these things called ZK snarks. You've heard about them mentioned in cryptography literature. So this is something that I spent quite a bit of time actually kind of working on all of the primitives to build up kind of these kind of latest bleeding edge ideas in cryptography. And I've kind of open sourced them under the, I'll put a link in this, inside of my company's organization for the Haskell ecosystem to use, because I think this is going to be a really, really interesting area that's going to kind of bear fruit and become as important to the internet as, say, TLS is in the future. It's just not there yet, but like we're so close. And I think if you look at kind of the trend line of how these things are kind of evolving computationally, like the cost of doing the proof construction is kind of going down linearly over time. And so by about the mid 2020s, like we should be able to do kind of, large scale zero knowledge proof evaluation for non-trivial circuits. And so take a look at this whole functional compiler that I've built. It basically takes this representation of a program that you describe inside of a Haskell AST and then compiles it into this circuit representation, as in like circuit representation as gates, logic gates. And then the evaluation of the function is then done by passing these specific inputs in this binary form through the entire circuit and then producing a cryptographic proof that you evaluate at the inputs to each gate, which propagate through the entire circuit, which allows you to produce a receipt of correct execution. So there's a whole actual Haskell framework that I built actually to do these kind of computations. And so if you're interested in this kind of niche area of computer science, then look at the repo there. So take a look, that's interesting. And if you're interested in cryptography, this is probably one of the most exciting areas to kind of work on. And you can do it in Haskell. So. Okay, and sort of the larger Haskell industry, I think this is something that's been kind of a point of some bemoaning in the community for a while, is that there's effectively no Haskell job market. Not to say that there aren't some Haskell jobs, but by and large, the industry has not been accepting of the language for various reasons. And it's not to say that it's impossible to find Haskell work, but your odds are quite low, just because of there's only so many. There's a lot more Haskellers than there are jobs, as you know. And part of that's just because the perception of Haskell in the industry at large is really not that good. So how do you fix that? Just have more success in the industry, and ultimately that will, counter the meme that Haskell is not suitable for production. That's the only way around it. I think if you are looking to do Haskell in the industry, doing this inside of big corporations is probably not the best way to do it. I think my experience personally is that generally large corporates tend to be a bit too risk averse, and the technology decisions tend to be dominated by economic factors that make choosing a functional language quite economically unviable. There are differing opinions of that, obviously, but generally speaking, most corporates won't use something that's not in the top 5 languages simply because that's just that's how IT works in most of the sectors. So, that kind of limits, the number of jobs that can be really created kind of to early stage companies and sort of small, medium companies. Not to say that it's impossible to do Haskell inside of a large organization, but it's bloody difficult to get buy-in from, N level of hierarchies of IT executives who are all just creating, what partner tells them to build and what tells them to use. So unfortunately, a lot of our industry is not very progressive as far as technology choices. I'll say it's impossible. It's just bloody difficult. So just be some straight talk there about what the truth is. So really, in order for Haskell, if you yourself want Haskell to be viable, like if you want a Haskell job, quite frankly, the only way to have a Haskell job is to create a Haskell job, and either by carving out a niche inside of a larger organization, which you can, hire and build a specific product that's, suited for Haskell. Obviously, don't use Haskell in places where it's not suited, but, if you have a project where, it could be Haskell could slot in there nicely and fulfill the needs of the business, then yeah, definitely do it. Or, we need to have more Haskellers to actually start companies. Quite frankly, more Haskellers need to create jobs. A lot of us are getting to the stage in our careers where we're, I've certainly created a company in the last couple of years, and, it's certainly a very difficult thing to do, but it's not something that's intractable. And certainly, within the grasp of a lot of Haskellers to start creating more, startups and companies themselves. And that will really be, even if you don't get to use Haskell, entirely, even creating a few jobs can go a long way. A few full-time employees can contribute back to an ecosystem in vast ways if they're given, the ability to kind of, add value to a business and produce open source Haskell. And that's really what drives our industry forward and what will produce more successful language, create more jobs in the future. So the problem I see right now is that basically the intersection of the set of, entrepreneurs and executives and people who are sufficiently studied Haskell to write it professionally is a very, very small intersection. And that section needs to kind of grow, and there needs to be more ambitious Haskellers who are willing to create companies in order for this kind of ecosystem to grow. And if that doesn't grow, then I don't I don't have high hopes for the language. So more people need to start companies. So okay, so here's the last optimistic slide. So Haskell in 2030. So here's my trite quote here, but programming communities always like to believe that our best days are ahead of us and that our worst days are ahead of us, but it's always the now is the problem. It's always been that way. So, Haskell is a beautiful language. It could have a beautiful future, but it's really important that right now we kind of don't accept the kind of status quo programming, that we have to believe that it can be better as an ecosystem. We have to kind of dream of a better future in 2030 and then start building that future today, because if we don't build it, nobody else will. So that's my last talk. Thank you. So I posted all of the links to all of the resources in this talk in this GitHub link. So if you have things fly by and you want to get the link to it, just visit this URL. I posted the slides there. And obviously, you can reach out to me on social media if you have any more questions. So, okay, so I'll switch back to the talk and then may I take some questions? Let's see.
Thank you, Stephen. That was very interesting. And we do have some questions. I can orchestrate them for you. First, we have a question from
sharing.
First, we have a question from Matt. So as soon as you're ready.
One sec, let me just turn off this. Does everybody still see my screen or do they see my face? Pause share.
I see the black hole.
Stop share.
There you go.
Oh, there we go. Brilliant.
Okay, so Matt has a question and I will invite him to unmute and ask you himself.
Hey, yeah, thanks, Stephen, for the really interesting talk. Yeah, my question is about the, given that one of the more common reasons for not using Haskell in production at some large companies is the potential for space leaks and the issues that laziness brings. Are there ways to add static checking to get around that? Basically, is this just a fundamentally hard problem that we can't solve at compile time in some cases? Or
So, okay, so the soft answer to this is that space leaks are a problem intrinsically to the language. They're a function or a feature of laziness or bug, depending on your interpretation. And they are avoidable, but you have to be able to kind of intuit where the allocations are happening in your program. And that requires a kind of fairly specialized set of knowledge about how to profile Haskell programs and where to put annotations. And a lot of professional code bases will do things like mark all constructors and all fields as strict and do other things like that as just a prevention for these things. But there's no way around it. You have to kind of intuit and understand how laziness works from the start when you're writing Haskell code, because that's part of the language, and that will come with time. And it's definitely, you can write production code which is performant, it doesn't space leak, and people have done that, and there are tools for profiling it, but there's nothing intrinsic to the language that you can use to prevent all these problems from the start. Obviously, there's some new strict annotations that you can put to do all of that kind of manual bang patterns automatically now, and that's definitely gets us a long way to kind of cleaning up the code base. But you still have to understand like when arguments are evaluated, when they're not evaluated. There's just no way around that. So, but I think space leaks in the industry are kind of grossly overstated. I think, for a lot of code bases that are, of a small size, they're not running constantly, it's Haskell just not going to space leak. You're in your one-off command line application that's running some sort of microservice if you write it effectively. So I think, it's a real thing and you definitely have to be aware of it, but don't let that kind of stop you from using language, because by the time you start being able to run in production, you'll be able to profile it and get those problems fixed eventually with enough time and expertise.
Okay. I think one of the maintainers of HaskTorch is in the chat, and thanked you for the shout out, by the way.
Oh, which one?
Torsten.
Oh yeah, HaskTorch. Cool project, yeah, very vicious.
Yeah. Maybe we'll do a HaskTorch talk in the future. I think that'd be fun.
Yeah, more Haskell machine learning. It's a great field.
Yes. Kevin has a question, but does not have a mic, so I will ask for Kevin. How could Haskell be promoted in post-secondary institutions? You have to solve all the problems tonight, Stephen.
How could Haskell be promoted in post-secondary institutions? So that means like university and the continent, right?
I guess so.
Well, it already is. I mean, there's a bunch of universities here in the UK that teach it. I know Imperial College does here in London. I know Edinburgh teaches it. So I mean, it definitely is there. I mean, how does it get done? I mean, there's a professor there that knows it and wants to teach it, barring that, there has to be buy-in from the computer science department there. I don't know the answer to this one because I've been out of academia for 10 years now, so I don't really know what the right answer is. But I think a lot of universities these days are kind of having this discussion about what their role is as far as like educating people for the workforce or educating them in theoretical computer science, and that's going to vary based on department. So if you happen to have a CS heavy department or CS theory heavy department, and they're currently teaching an imperative language, then maybe having an intro to functional programming course would be a good way, even if it's kind of taught by a grad student or taken as an elective. But I don't have the answers to that one. I'm just kind of speculating here. But teaching Haskell is a more there's a famous letter from Dijkstra where he talks about the particular reasons for switching the University of Texas over to using Haskell, which I think is a very compelling argument that he wrote to the department. So maybe look at that as an example for how to convince academics.
I'm really glad you mentioned the Dijkstra letter. I was just about to mention it myself. I think maybe they had switched from Haskell to Java, and he was writing in response to that, like such a bad idea, and here's all the reasons.
Yeah, somebody should link it in the chat there for everybody.
Yeah, someone link that in the chat, please. You'll find it in 2 seconds of Googling, I'm sure. Joe Kachmar, a friend of the meetup and former speaker, has a question. Joe, go ahead.
Hi, Stephen. So I've got this sort of, I guess, maybe kind of squishy question about Haskell community organization and things like that. One of the topics you touched upon was sort of the fact that you've got this fractal nature of how all of the GHC extensions change the language. And necessarily, I guess what I've interpreted as the fact that the language is sort of driven by people who want to explore new things and people who want to put in some work, kind of maybe build up enough effort to get these things through. And it seems like it's been very difficult to sort of have centralized, coordinated, standardized change and evolution of Haskell, the programming language. And that kind of means that it's difficult to make progress in consolidating some aspects of the language that might make it easier for people to write tooling or sort of understand completely. Do you see a way for the Haskell community to sort of progress towards this direction of maybe becoming a bit more standardized? I mean, do you think it's even a good idea? And do you think that, I guess, given the fact that the Haskell community tends to be fairly independent, and I'll say like, not necessarily essentially coordinated to some other programming languages, that's something that, is helpful or a hindrance to the language long-term in some of the topics that you've touched upon?
That's a hard question. Yeah, that's a good one though. So your observation is correct, actually. Haskell is not centrally organized. It's very decentralized. Haskell is, somebody best described Haskell to me, the ecosystem as it's not led, it's maintained. There's no uniform leadership of the Haskell community. It's a very organic effort in many ways. If you think there's one person that leads Haskell, even Simon, it's not really the case. Certainly GHC development is a, yeah, I mean, the prevailing philosophy on this for the last 20 years has been, if you do the work and you can add it as an optional flag, and it doesn't break anything, then you can add it. Effectively, that's been the kind of prevailing philosophy, and that's given us a lot of things, letting the language kind of evolve forward. But it's also come with some additional complexity to the language, which has basically been, managed by the GHC developers quite well, effectively. But you're right, Haskell, as we write it today, is a beast. It's a very complex amalgamation of all of these extensions, and if I were to answer your question, I don't know the right path out of this. I don't think anybody does. I think there's a lot of what's the most delicate way to put this? There's a lot of thinking that, there should be probably another specification, Haskell 2020, which consolidated a bunch of what became the core language so that we're not so much dealing with, this entire amalgamation of opt-in features of this blessed core of things. So the only reason that hasn't happened is that really nobody stepped up to do it. because it's, it's quite a bit of work, and I don't think anybody really has the time or the effort to actually do it. So it's not a function of the fact that it can't be done. It's the fact that nobody's really stepped up to do it, because it's a fair bit of work and does involve a lot of, a lot of cat herding to do that. So I don't have the answer to that. I think that's part of it. And I think as an ecosystem, we're just gonna have to figure that out, because I think nobody thinks that the current path that we're on right now is the most sustainable thing ever. I think even PhD developers would say the same. But, so sorry, that's the non-answer to it. I don't have the answers to this, but maybe somebody else will.
I guess I appreciate that. I think that even is helpful. But I guess my follow-up, and if you don't have an opinion on this, feel free to punt. Because I'm just asking two questions now. Basically, would be, I've noticed that C++ obviously has progress on this because they went through a dark time of not being able to get a proper standard out, and C++ 0x to 11 was rough. And they seem to have gotten on a good cadence now, and the Rust community seems to have gotten into a good place, although they kind of started off there. Are there any lessons that you think that the Haskell community might be able to take from the progress made in C++ and sort of the way that Rust has organized itself, or do you think that the community concerns and organizations are just too different, and we're going to have to kind of try and find our own way?
So I used to engage quite a bit with the C++ community, and so largely what happens is that a lot of large corporates end up contributing a significant amount of time and full-time engineers to contributing to the language standard. So if the Haskell community wants the language specification to come together in the manner of C++ and Rust, then probably more people are going to have to be paid to work on it full time, because I think honestly right now the biggest thing is that there's just not enough time for everybody to do the work. So there's probably 100 times more Rust engineers that are getting paid to work on the Rust compiler at least part time than there are Haskell engineers, and that's honestly I think it comes down to just money and jobs. People are not given enough time to contribute back to the ecosystem, and there's a lot more C++ users in the industry, and there's a lot more, small margin more than there are Rust developers than there are in the industry. And Rust has a lot of just seed capital that went into that language. Turn out if you pump $10-15 million into a community, then yeah, they get a lot of nice things. Funny how that is. So money, sadly.
Thanks for the thoughtful and nuanced answers. I appreciate it.
Thanks, Joe. What happened to Haskell Prime? Wasn't there meant to be a kind of ongoing revision of the language specification?
No, there was an effort to do a Haskell 2020 specification, but yeah, I think it's kind of dried up a little bit with the interest on it, because it's a fair bit of work to do kind of a consolidation of language, and what the language should be ultimately is an open question. And I think different subsets of the community view it differently, and they have different incentives about what should be in the core. And you can go track all of that, all of the machinations on that back to the mailing list and see how that kind of went. But ultimately, more people need to have enough free time to kind of contribute back to the ecosystem to do that. And I think not a lot of people have the free time to do that, fortunately. So
I just have one question, kind of related, not exactly to Haskell Prime, but to Haskell, the language, how it's used. Do you have any opinions about this simple Haskell idea that's just recently sort of emerged? It sounds like you do.
Okay, so it's a delicate one. What's the most nuanced way to say this? I think everybody that uses Haskell industrially within a team will eventually have to decide for themselves what the right ceiling on abstraction should be inside of your code base, because Haskell as a language basically has this near infinite ceiling on abstraction where you can get all into this kind of stratospheric level of abstraction, where you're talking about all sorts of abstract ways of preventing, runtime errors, and there's a lot of complexity that can add to a code base. And I think part of what good software leadership is inside of a team is basically figuring out with the engineers involved, what specifically are the kind of cases that we want to offload to the type system, and what once can we handle at runtime, and what's the right level of abstraction and tools to be used inside of our code base, inside of a corporate code base. So I think a lot of people that are talking about simple Haskell are coming from a good place where they've experienced that gone wrong. And there's been a lot of kind of cases in industry where some Haskellers, when they're given their first Haskell job, kind of go crazy and end up building these abstractions, which are kind of these, castles in the sky of abstractions that don't really add value to the business, and they kind of distract away from the day-to-day development, and that can often end up very bad for the business. And so I think some of the people that are talking about that are particularly referring to that phenomenon. However, I think the best way to address that phenomenon is really not to, fundamentally carve out a subset of language for the entire ecosystem to use, which kind of limits us down to, what subset we should all use as a community, but to figure out what it is in the context of a specific corporate code base, and like what particularly are the, invalid states that we want to make unrepresentable in our code base. And I don't think you can do that on an ecosystem level. And I don't think that limiting the amazing tools that we have inside GHC in general is a good idea. I think we have amazing things like, type families and all this, pseudo-dependent type machinery that we can use to build powerful abstractions. And so long as they're nicely encapsulated and they actually add value and, restrict the invalid states in the code base, then I see no reason we can't use all of the advanced features, so long as they fit in their place and they don't leak and cause unnecessary complexity. So I will say that a lot of people have been trying to where the abstraction I kind of in my corporate code base that I've drawn on is I don't try to add tools to the language, which try to route around GHC problems themselves. So like I wouldn't build a whole language or whole corporate code base that happened to use things like extensible sums or something, or try to fix the record problem in user space. I don't think that. Well, I think ultimately you're routing around a problem that's intrinsic to the language and trying to reinvent subsets of GHC. And I think that ultimately just causes more pain than it does. But that's my personal level of abstraction. Obviously, there are different code bases that have taken different levels of acceptance for what they will allow in the code base. So that's my answer to simple Haskell. I think it's coming at what I think is ultimately an economic problem and trying to address it as an engineering problem. When I think you actually need to figure out the fuzzy people problem associated with it first, rather than trying to solve it with more code. Does that make sense?
Yeah, completely. It's always seemed to be a cultural problem. There's always one group of Haskell programmers. Everybody really wants to write Haskell at work, but one group of programmers thinks the other group of programmers is ruining it for everybody else. And it's interesting actually having now seen your talk to see there's a further complication in that we'd like to use Haskell at work. We want you to tell us how we can convince people to do that. But there's no really easy way to convince anybody when there aren't clear use cases and we don't even know what it would be like to build such enormous systems in a functional language. So maybe you figured out the only practical solution, which is to start your own company, as you said before.
That's a solution. There are other paths to that, but yeah, the more Haskellers need to take up leadership positions, start carving out, projects that they can work on inside their companies where Haskell can add value, and only carve out, places where it can add value. Applying Haskell in places where it's not suited doesn't help anybody. It doesn't help your employees. It doesn't help, the ecosystem at large. It ultimately just creates more churn. So, it's a fine art. Yeah,
and then having done so, you can enforce whatever you think simple Haskell means. And this is just a matter of deciding how you want to use the language. Like you would decide any language. What is acceptable code style for you?
So this is not new to Haskell. I mean, the C++ ecosystem has this in large. I've never met two C++ engineers that agree on which subset of the language to use. And, C++ specification is vast now. Not quite as vast as Haskell, but, this is a problem they encounter over there as well. So this is not unique to Haskell in many ways.
So KK has a question.
Cool.
Go ahead.
Hey, Stephen. Hi. Yeah, my question is regarding your slide on algebraic effects. There you mentioned two libraries there, which are quite nice to get into. Just wondering whether you have a personal preference over polysemy or fuse effects.
Yeah, so I've played around with all of them. I kind of did a write-up on them that I put in the links inside of my website, where I kind of compare and contrast all where I kind of compare and contrast all the features of them. So I've used polysemi a little bit. It seems to be the one that kind of had the lowest barrier to entry for me to kind of get something up and running on it the quickest. And I took a look at the code base. It's quite concise and quite clean. So polysemi is probably my go-to algebraic effect library at the moment.
Cool. Okay. Thank you.
I've got a question.
Hello? Someone else is there?
Oh, yeah, I'm just lurking here with the question.
Can you type it into the chat?
Oh, yeah, sure.
Thank you. Just we have a list of people. I want to be fair. Alex does not have a mic, so I have to ask Alex's question. What do you think about the Ada language? We should probably tell people what Ada is. Is that Haskell for Java? Or is that Frege? I can never keep these things straight in my mind.
Is it ADA or ETA?
ETA, ATA.
Oh, ATA, the one targeted at JVM. Yes. So I've not used ETA, so I'm going to talk purely on like a surface level about it. I don't believe it's currently maintained anymore. I know that there was a company or startup that had gotten some initial capital to kind of look into building some sort of consulting business on top of that out of India. But I think that more or less dried up a couple of years ago. So it was in the Haskell-like family, if I recall correctly. There were some extensions to the language which tried to fix a few things. So it wasn't like drop-in compatible with GHC itself. So I've never used it in particular, but no, it's cool. I mean, it would be lovely to have a Haskell-like language which compiled to the JVM. So like I applaud that kind of effort, but maybe probably going about the route of kind of building a superset of a subset of Haskell is probably not the right way to go if you want to, basically, take Haskell code in the ecosystem that already exists and transfer it over to a new target. Maybe just build like a new JVM target to GHC. But this is all a hypothetical discussion because I think I've never used it. So that's my kind of uninformed opinion. So sorry.
Joe now wants to hear your thoughts on the Ada language. since we brought it up.
The only person I ever used to know is an old coworker of mine who used to work on like airplane control systems, and he used to do a lot of Ada. So Ada used to have some really cool features where you could do things like specify linear constraints on integers. So you could define something that was like, a range value, which is very, very cool. We still can't even do that in Haskell without things like refinement types. So that's a very cool feature. However, I have not written any Ada as well. I know it's used heavily in avionics, but it's certainly an interesting point. It's obviously used in a lot of high assurance systems, but I don't know enough to comment beyond that. So try it out yourself. I don't know.
Okay, I totally walked into that one, Eta versus Ada. I've heard of Ada, but I haven't even thought about it in the longest time. So Jeremy M, would you like to unmute and ask your question?
Sure, yeah. There was recently an argument in a blog post. Better?
Yep, sorry, you're very soft.
There was recently an argument in a blog post about people that learn Haskell as a second language had a interesting journey in learning about several FP concepts and are maybe therefore better suited as employees. So following this argument, companies should employ Haskeller language enthusiasts. What do you think about that?
I didn't catch the word you say, something concepts.
FP.
So people that learn Haskell as a second language have an easier time grasping FP concepts. And so that a company should employ people that know FP because they make for better employees. Is that the crux of the argument?
Yeah, that companies should employ FP or Haskell in general employees as they, how do you say, they dive deeper into the language concepts. They had an extensive journey than in your average developer, let's say.
Well, okay, so this is kind of a soft question. It's a very humanistic one. I think as software engineers, the more theoretical concepts that you've kind of cut your teeth on, the better you are as an engineer, not just FP. Like personally, when I get a CV or a resume on my desk for a potential hire, like the first thing I look for is that they have a breadth of experience across a variety of programming languages, and like the more kind of paradigms, the better. So like if you're learning Python and Ruby, those are basically the same language, right? If I see that you're learning Ada and Prolog and Lisp and Haskell and Scala, that says you kind of have a breadth of kind of intellectual range that you can kind of conceive of different ways of approaching problems in programming, and so that can only be a good thing. I don't think it's limited to FP. Obviously, software engineers that have learned multiple programming languages in multiple different paradigms are that's obviously they're just more exposed to more ideas, which only makes you a better programmer. So yes, you should hire people that have or you should look for people that have a range of experience across a variety of tools and not just hyper specialized in C# or something. That's the sort of truism answer.
Okay, next question is from Thales, who also does not have a microphone, so I'll ask, for which use cases would Haskell be a bad fit?
Oh, that's a good question. Anything real time, as in like real-time signal processing or anything. Obviously, you have to manage runtime, so you can't be doing things that are going to have a failure mode if there's a garbage collection pause. So that's out the door. Anything where you have to do a lot of work on the Windows operating system. I think Haskell on Windows is just a well of sorrow that I wouldn't wish on anybody. I think ultimately the only way to solve that is to basically just pay a lot of engineers to kind of port portions of the ecosystem over to Windows, and there's just no way around that other than just pumping a lot of cash into the ecosystem, unfortunately, and that has not been done yet. So I think if you're trying to do development on Windows, God have mercy on your soul. Other than that, I'm not particularly a big believer in Haskell on the front end, in the sense that like Haskell transpiled to run in the browser. I think I've seen a lot of companies that have kind of tried to build those kind of solutions, and they've kind of ended badly in most of the situations I've seen. So I think that's one that you have to be. I'm not saying it's impossible to do, but I'm saying that like you're buying into a very, very, very niche ecosystem if you're taking like a high-level functional language and then compiling it into JavaScript to orchestrate your whole user interface. And I think that should be done with a bit of caution that you're going to be able to support this kind of code base in the future. Anything else? I think any kind of backend service, any kind of web architecture service that's basically running in some sort of serving user requests, talking to a database, processing data, I would say it's well suited for. That's a lot of what software these days, CSV comes in, JSON comes in, IO comes out, those kind of things. I wouldn't use Haskell for interactive data science either. I think the kind of code that you often write inside of say an IPython notebook is very kind of ad hoc and loose and very dynamic and dynamically, or it's very intrinsically dynamic. And so when you try to write this kind of if you ever try to code like a data frame inside of Haskell, you'll hit up against limitations of data frames are intrinsically very dynamic structures that are very hard to encode in Haskell, because ultimately they're you either encode everything as this giant sum type of any possible value I can deserialize from a data source, or and then it becomes very hard to kind of write type safe index queries over data frames. So things that you would code as ad hoc IPython pandas workflows, I wouldn't particularly do in Haskell. I think it's just not, the language is not well suited for that. So those are the kind of the four areas that I wouldn't use it. Anything real time, anything like front-end web development, like user interface in the browser, and yeah, anything. Yeah, those are the areas. No interactive data science.
Okay, thank you. So next is Tom. Tom, do you want to unmute, ask your question?
Sure. So my question is, once you've climbed the Haskell mountain and you're faced with, well, you're kind of faced with a multitude of things you could choose to go down, but like two kind of typical paths are either category theory or proof assistance. I'm wondering which one was more mind expanding. I know that's kind of a vague word, but like mind expanding in the sense of teaches you things that you never even knew existed.
Okay, so yeah, the thing about the Haskell, like once you climb the Haskell mountain, you realize there's always another kind of mountain that's just beyond the peak right there. And like once you get to that mountain, there's another peak too. Which actually makes the Haskell like quite interesting because you'll never reach a plateau. Like there's always the next level you can go to. And like I've certainly been doing Haskell for 10 years now. I still feel like a novice at it. So what's the most mind expanding thing? So on the category theory side stuff, so I did a little bit of that. I wouldn't say I'm an expert by any means. So the amount of category theory that's actually directly applicable to Haskell is not that much. I think if you like read the canonical textbook on category theory, like Audi or something, like the first 3 chapters are things that you can kind of encode in the Haskell type system, and it's even questionable whether a lot of those constructions are well formed inside of Haskell. But the applicability of things like beyond say like understanding what adjunctions and con extensions and monoidal categories are is very limited. And I think there's a few Haskellers that claim that category theory is kind of an inspiration for the design of their programs, but that's a very small group of people. I think most real world Haskell is not informed by category theory at all. And I think it's an interesting subject to discuss if you're a pure mathematician, because it gives you kind of different ways of mapping concepts between different branches of like mathematics. But unless you have a particular interest in say like algebraic topology or group theory or, and you want to discuss those kind of concepts in a categorical context, you're not going to find a whole lot that's very applicable to Haskell. Other people may disagree, but I think, you just don't use category theory all that much in Haskell. And then crypto systems. So I've done a little bit of this myself. I think it's an interesting area. So I'm not an expert by any means in cryptography, but I've done a fair bit of work on that verifiable computation stuff. I think my work has not been on building like new crypto primitives or anything. It's basically just been building on this compiler that I've been building for zero knowledge proofs for a while. I'm mostly interested in that from the compiler perspective because there's a lot of very, very interesting optimizations that can be going on to build these kind of more optimal circuits that I think Haskell adds a lot of value to. And it gives us a nice way of kind of expressing the right composable crypto primitives together to give rise to some really interesting things, which you'll see in that code base if you check it out. But yeah, certainly cryptography it's a really nice application of like abstract algebra. So if you're interested in that, then you'll see things like, extension fields and finite fields and, Galois groups, and they'll be directly applicable and you can code them directly in Haskell. And it's actually quite lovely. So I think cryptography is kind of a next step if you happen to be a Haskell programmer and you happen to have some interest in abstract algebra, because that gives you something directly to apply it to. So I'd say probably cryptography is probably the more directly applicable if you happen to be looking for something new in mind or something mind expanding. Category theory is enriching in and of its own way, but probably only if you have an interest in pure maths.
How about homotopy type theory or cubicle type theory?
Yeah, I'm going to pass on that one because that's
you get really outrageous stuff going on.
Ask somebody else on that one. I'm not going to comment.
That was just me being funny. So we have a few more questions, but I don't want to make presumptions on your time. Are you good for now, or should we put a cap on it?
I can take a few more questions, actually.
Okay, cool. Then Benjamin has a question.
Hi, Stephen. So what is today what Haskell had been 30 years ago?
What is Haskell today that had been 30 years ago? Can you elaborate a little bit? I don't understand the question.
No, I mean, what Haskell has been at in 1990. What is a language in that state today to you?
Like, what was it back then to me?
No, I mean, which language has a similar fate that Haskell had 30 years back?
Oh, what language had a similar fate? I think Haskell's trajectory has been kind of very unique in the whole programming ecosystem.
Yeah.
It's, don't say Perl. No, I wouldn't say Perl. But yeah, I mean, Haskell started as an academic language, which kind of like found its way into industry very, very, very slowly. And it's been kind of an up and down ride in industry, but it's primarily been an academic language. And I'd say most of the work in Haskell has been done from the perspective of producing new research and new papers first, and then producing industrial code second. So the only other language I probably would compare it to in that sense would probably be things in like the ML family. So like OCaml came around as kind of an extension of like MiniCaml, which came out of the French research universities. That trajectory has been kind of comparable. I think OCaml and the whole ML ecosystem has been kind of on a similar trajectory as Haskell, but it's been very kind of a slow, steady state rather than like languages which were contemporaneous to Haskell would be things like Java and Python, which have certainly seen, you know, massive growth in the last couple of years. So, but largely because they're in a different paradigm. They're, you know, first and foremost quite small languages, and Haskell is not a small language.
Okay, the next Chaba has a question.
Chaba.
Hi. Do you know stories when Haskell was replaced with another language in a successful industrial project?
Haskell was replaced.
Yeah, the project was successful, but anyway, Haskell was replaced with something else for some reason.
Yes, many. I think this happens a lot with kind of early stage companies where either the initial prototype of the product was written in Haskell, and then once there was a change in management or change of executives, they basically took all the Haskell code and burned it to the ground and then replaced it with Java or Python or JavaScript. So I know that there's definitely been some companies in the States that have had that fate that I can't mention names, but I know that there was a very high profile compiler project out in California, which was replaced, which is a hardware compiler project, which was replaced with Rust at one point. Yeah, I mean, there's the whole annals of Haskell being used in industry are basically mostly failures. There's a few successes, but they're isolated, and it's hard to say whether that's directly correlated to the language, because a lot of industrial code bases kind of go through this infinite cycle of birth and rebirth. So I wouldn't read too much into the fact that Haskell has been swapped out, because if it were written in any other language, probably would have been swapped out as well. But, you know, I don't know a whole lot of like long running code bases which have been Haskell from their conception, which have been kind of running for multiple years that kind of power core infrastructure inside of companies. There's a few inside of a few banks here in the UK, which have been kind of doing that for a while. But the banks are kind of a special place where a lot of things can kind of live forever because of externalities to the code themselves. But yeah, there's quite a few cases where Haskell's been replaced. What I'd be more interested in is the case where there was a Java code base or like a C# code base, and somebody came in and replaced it with this really nice clean piece of Haskell, then it succeeded beyond everybody's wildest dreams. If there's a case study like that, you should go public with that like immediately, because that would be amazing for everybody. But like the history of Haskell is one of either quiet successes or quiet failures, sadly.
Yeah, people really need to brag about this stuff much more.
True.
Okay, if there's no follow-up, then KK has another question.
Yeah, hey. Yeah, my question is regarding the computational integrity proofs work. Since the community of cryptographers are, rather risk averse, so they tend to advocate not rolling your own crypto and to stick with tried and tested algorithms and then libraries. Given that, might they view the choice of language, Haskell, which is not so established for cryptography after all, with the exception of maybe kryptonite, might they view the choice of Haskell as the language sort of hard to justify, for working on this? That's the first question, and a follow-up question is regarding Rust being quite popular at the moment for doing crypto work, and what you think is great about Haskell that makes it better for the task than Rust even.
Okay, so let's unpack the cryptography thing. Yeah, you're right. Crypto is basically hazardous material that you should be very, very careful when writing, especially for things like interactive protocols. So if you're writing like a TLS stack, be very, very careful if you're writing it inside of a high-level language, because there's all sorts of subtle things that you can introduce, from timing attacks to different side channels. Like, it's very difficult to get crypto right, and so you should use kind of the most boring vetted library you can possibly find, which is probably some C code which has a lot of inline assembly in it. That's kind of the state of the art as far as crypto goes, like, because you can drop down to the assembly level and then code constant time operations on your elliptic curves and things like that. However, if you're building things for non-interactive protocols, so things that are not client requests, token sent over here, verified, things like our research problems, like the ZK-SNARK stuff that I'm working on. This falls into the realm of things that are woefully impractical to do at the moment, because they're so computationally involved. So like the proof generation time for a non-trivial ZK-SNARK circuit can take like hours to generate. So if you're running timing attacks against a computation that takes 3 hours to generate a proof term for you, it's insane. You're like, timing attacks don't really actually occur in the real world. So like for that kind of research problem, Haskell's fine. Just like any language is fine, because it just has to stand up and work end to end. It's not being used interactively over the internet. Then it's fine for that kind of research domain. But no, you're right. Generally, if you're building things that like are doing like block encryption, or you're building TLS or something, then yeah, probably drop down to either bindings to something like Google's cryptography primitive libraries, and then wrap that up inside Haskell. But don't roll your own custom crypto in Haskell for non-research problems.
Yeah, that
the question was about Rust as well. So for, like I said, for this kind of research problems, whatever you can stand up the fastest. So intrinsically, these problems are very algebraic in nature. So like if you want to use Rust for that, maybe it works pretty well. I think Haskell works pretty well for these things. Rust is basically marginally better C++. If that's the kind of code you want to write at, then for certain problems, that's particularly a good choice, I guess, if you're working at that level. If you want to work at a high level, choose a language like Haskell. Whether you should use which one's good depending on which domain you're working in. For crypto stuff, probably don't use Rust. Probably drop down to C and inline assembler, because that's what all the tested libraries use.
Sure, yeah, and for the work on the SNARK stuff specifically, did you find that Haskell has nice ways of, like, I don't know, encoding the algebraic properties of these things, for example?
Oh yeah, the Haskell code for that stuff, for coding the algebraic structures, is beautiful actually. So I worked with a very lovely mathematician named David. Actually, he wrote this library called Galois field, which I'll post a link to actually it's in the links on the slides, which encodes these finite field objects as this very nice type safe interface, and you can run quick check tests over it and like generate all of these composite extension fields over elliptic curves, and the code is super concise and lovely to code. It doesn't require any template Haskell or anything. It all just maps beautifully to the type system. It's a very beautiful library. So I think Haskell is really nice for representing these kind of algebraic structures that occur in cryptography research, with the kind of caveats that like the operations aren't constant time or anything, but for the star stuff, it doesn't matter.
Very nice, thanks.
I think our last question tonight will go to Tom.
Hi. Yeah, so my question, so when you apply for a job which isn't Haskell and you say you can program in Haskell, you quite often get that blank look on the hiring manager's face and you feel like a bit of an alien. And also the kind of the coding challenges are they kind of are biased against programmers that take time to think about this solution. So like, I guess in a way I'm trying to say, how do you communicate the skills that learning Haskell gives you to people that don't really know what Haskell's all about? It's quite a vague question, sorry.
So there'll be kind of two different answers to this one. One is where you're applying to a job where Haskell will be used, and the other one's where you're applying to a job where Haskell will not be used. For the one where it will be used, obviously it's a strength, and you should probably focus on, your particular, affinity for the language and why you like to use it, and the value you think it brings to the business, because that's what they're looking for. If they're hiring other Haskell engineers, they're looking for somebody who kind of groks where to use Haskell and understands the kind of strength and benefits of the language and what it brings to the table. If you're applying for a job that doesn't use Haskell, then I think you got to really kind of step back and realize that like a job is inherently like a transactional thing. Like your hiring manager is basically looking for somebody to fill a role to produce a certain amount of value for the company. And they're not, if they're like most managers in the industry, they're not going to really care about the means that you do that. They're just going to care about the specific applicability of your skill set to the problem that they have at hand. And so like if you're interviewing for a position, you should, phrase your skills in the way that addresses the needs of the business first. And if you can kind of form Haskell and your knowledge of functional programming in a way, that, adds value to the company, then that's the best way to approach it. Because that's what he's looking for in a job or hiring transaction with you, because he's looking for somebody to fill a role. So.
If I can just add from my personal experience, I've never had a Haskell job, but in interviews I mention it, and I think it can get you some credibility. You may not be applying for a job where you will use Haskell, but the fact that you're interested in it and you bothered to learn it, it can be an interesting conversation point. It could potentially impress your employer that you have the capacity to learn different things, even things that are like well outside your role. So you don't necessarily have to use Haskell on the job to get some mileage out of it in practical getting hired terms.
It's really a strength.
Yeah.
I agree.
So we don't have any further questions, and I think we've taken up enough of your time, which you've been very generous with tonight, Stephen. There's one final comment, and I think we can all agree it'd be really nice if at some point you could give another talk about your work at Adjoint. So even if there's maybe this pessimistic quality to part of your presentation, you have clearly personally invested heavily in the future of Haskell.
Yeah. So my work at Adjoint, my company does really, really boring kind of business-to-business software. So we build accounting solutions that allow multinational corporates to better settle their accounts with each other more efficiently. So it's the kind of really, really kind of boring back office stuff that happens inside of large financial institutions. And we use a little bit of Haskell to automate that whole process. And so that's what I do. So I'm a CTO, so I oversee the engineering efforts on that project. So I'd be happy to go into it, probably not in a Haskell talk because it's kind of just boring business.
Well, we would love to have you back again at some point. Maybe not in 10 years, maybe sooner than that. In person, even better.
Thanks, everybody. It's been great having a talk with you this evening. Hopefully you got something out of the slides, and hopefully hopefully we can make Haskell better in 2030 than it is in 2020.
Yep, we should all contribute to that goal together.
Yes, open source, that's the key.
See you again someday soon, I hope. Maybe Zuri Hack, who knows?
Yeah. Okay, everybody.
Okay.
Have a
Take
good
care,
night.
everyone. Bye-bye.